10:30. Good morning, everyone, and we'll go ahead and get started with today's presentation. Today we'll be covering the digital twin and how the digital twin is really your crystal ball for manufacturing. So I'm Nathan Pfeiffer. I'm an account manager for Geometric Solution. In today's presentation, we'll be covering what is the digital twin for manufacturing. We'll talk about some solution overviews, and tools used for the digital twin in manufacturing, and also some case studies that my company and our parent company, Walt Engineering, have done with the digital twin. So as I mentioned, we have a parent company named Walt Engineering, and they're located out of Warren, Michigan. And so we have several offices spread out across the Midwest. I'm in Cincinnati, Dayton area. We have offices in Indianapolis, Chicago, and Minneapolis as well. And Walt Engineering uses Siemens software for actual engineering work that they do day in and day out. They do consulting work for companies like GM and General Dynamics Land Systems. So not only do we sell Siemens solutions, and this is the Tecnomatix suite, the digital twin, we also use them on a day in, day out basis. We have over 300 workstations, almost 200 employees, nearly 300 seats of CAD, PLM installs across the board. But what's really important is the Tecnomatix suite, which we're talking about today over on the right side, and that's the digital factory. And we own seats of that, like Process Sim we'll be covering, Plant Sim, Variation Analysis, that's VA or VSA, just to name a few we're covering. So we'll start today's presentation by talking about risk mitigation. So you and your companies are faced with many different concerns and drivers. From an industry perspective, you have compressed timelines. You probably see a demand for increased quality. You have to lower costs, increase productivity, and you certainly have to innovate as well to stay ahead. I apologize. I think my audio went away there for just a second. As far as an engineering level concern, we have validated processes concerns, cost overruns, production targets, launch delays, and enhanced flexibility that we need to maintain. So the question truly becomes, how do you mitigate your risks? How do you answer all of these things and stay ahead of the game? And that leads us directly into the conversation about what is the digital twin. The digital twin is your manufacturing facility simulated in a digital enterprise. Everything from the entire plant itself, from the products coming in the door to leaving on semi-trucks, to individual processes like spot welding, and even all the way down to at the product level or part level, validating those parts. And so, like I said, we refer to the crystal ball as the digital twin because it allows you to see, or we refer to the digital twin as the crystal ball, because it allows you to see problems that you could have before they actually happen. And these problems include increasing hourly throughput, identifying bottlenecks, assuring your robots can reach everything, getting your products to market sooner, ensuring the quality of the parts that you build, validating that your product actually works, and finally validating production quality from your office. In the description of this webinar that you've registered for today, we talked about how quality can be monitored from the executive level all the way down to the individual engineer working on the part. The executives of your company using these suite of tools can see the quality of each product going out the door. So for each of these products, they have a different sweet spot, if you will. The first is plant simulation. This is what I mentioned. This is the entire plant simulated. As you can see here inside the crystal ball, there's a little video rolling of the entire process, even people being modeled that are walking around. And plant simulation helps increase hourly throughput. It'll help you identify bottlenecks, get your products to market sooner, and validate that your product actually works. And we'll take a deeper dive into each of these products as we move forward. The second product we'll be talking about is Process Sim. And Process Sim is an individual process. For example, it could be spot welding, or it's at the cell level that we're analyzing this and making sure everything works correctly. It too can help us increase hourly throughput, identify bottlenecks, assure robots can reach everything, get your products to market sooner, and ensure the quality of the parts that you build. After that, we'll be talking about Mechatronics Concept Designer, or MCD for short. And MCD enables us to increase hourly throughput, identify bottlenecks, early product launch, and validate your mechanical product actually works. You see there's a bit of overlap, and I'll explain the differences between each of these and why these are still the sweet spot for each one. After that, we'll cover variation analysis. You'll hear this referred to as VA, VSA, a variety of names, but this is variation analysis. This helps early product launch, ensure the quality of the parts you build, and validate production quality from your office no matter where you are. And then the final product that I'll give you an overview of today as part of the digital twin suite of solutions is DPV, or Dimensional Product Validation. And this too is about the quality of parts you build. And this is really the tool used to validate production quality from your office. And I'll explain that as we move forward. So as I mentioned, as we roll through all of these and I talk about each of these products, I'll show you some case studies of work that we've done. As I mentioned, we're an actual engineering firm as well as selling these suite of Siemens solutions. So we'll start with plant simulation. Again, this is your entire manufacturing process simulated in our crystal ball, or the digital twin. So the first example we have, this is we joke that this is a barroom napkin sketch. This is a sketch of this company's process as it is today, and they were a TV manufacturer, and they wanted to add a brand new 3D stereo that you see in yellow at the top to their existing process. Well, that can be a little difficult because you notice in yellow, once we overlay Tecnomatix and plant simulation on top of this, you notice in yellow that there's a blockage in the assembly line. So we use this tool to analyze things like, do we have too many carriers, not enough? Is our line speed too fast? And we run these experiments of throughput per day to get the most effective process possible rolling for us. And we'll experiment with quantities of carriers from 10 to 100 and increments of 10. We'll also talk about conveyor line speed from 1 to 5 meters per second and see which gives us the best possible solution. And again, this is all done inside the software before we ever change anything or add the 3D stereo out on the plant floor. We can predict these things. So again, we've run the simulation here, and we can begin to look at the output and the information that it gives us based upon the different experiments that we've run. And you see here, this is a table, but we'll switch over in just a second to a graph that shows the information a lot easier. And you can see it looks at about experiment 12 that it really peaks as the most possible throughput per day. And that's what we want to run and implement in real life. And that's why this is the digital twin. So we scroll down to experiment 12, and you can see that we have about 2,300 units per day, and we actually had to decrease the line speed from 5 meters per second to 2 meters per second. And I know that seems counterintuitive, but that's the information Tecnomatix gives us, is that the fastest line speed isn't always the best for what we're doing, that we may need to slow it down, and there's a certain number of carriers as well. So again, this is a company, and through several of these, I apologize, I can't give the name of all of them. You'll recognize many company names as we go through, but some of them will have to remain nameless. And for this one, once we helped them and did this plant simulation, we increased output by 16% without adding any people or any equipment, and that includes adding in the brand new 3D stereo system. We optimized the number of pallets and conveyor speed, and 318 additional units per day went out the door, increasing profit by more than $15 million annually for this particular company. And this is what happens when you simulate or use the crystal ball to see what's going to happen when you add a new part to your line. This next one is a large food manufacturer of chips. They do chips is about all the information I can give you. But they were going to build multiple eaches plants that will distribute to mom and pop grocery stores, like the little ones that I'm sure if you live in a small town like me, that you have, those little grocery stores. And but by eaches, we mean variety packs. So one of these, one of these, one of these. And so this chip manufacturer planned to create more than 90 local eaches plants. Well, after running Tecnomatix and plant simulation to create the most efficient plant design possible, they realized in order to effectively distribute and get their product to all these local mom and pop stores, they only needed 63 plants. If you think about it, we saved them 30 plants being built. That's millions of dollars per plant because they weren't created. The next product we'll talk about is process sim. And again, this is, as its name suggests, an individual process like spot welding that you see in the video there. So I like to start in showing you a brief video about automotive manufacturing in the 1970s. And we talk about that quality of parts is really important, and having things we can measure and identify exactly what's going on out there on the plant floor. Obviously, in this old style, that wasn't exactly the case. And we're going to get to a spot here in a second that really interests me, that shows how far we've come in measuring quality and exact things. And what the digital twin can provide for us is this digital overview. So we know exactly what's going on out there. You even see two guys handling that side of the car themselves. Again, this man putting things into the fixture right here, but we're getting to my favorite part of the video in just a second. Again, it's going to be a guy with a hammer, and he's going to create some curvature in a particular part. It's not exact at all whatsoever. And it astonishes me how far we've come with the robots that we have in front of us today. And if you think about it, in just 40 years, here's the guy with the hammer, and it's going to be right there. You saw that curvature he just created, just not exact at all whatsoever. So where are we today with the digital twin? This is what it looks like out there, and here's what it looks like inside the digital twin solution of Process Sim. Robotic simulation is now an integral part of body construction processing that we have and do today. You see here, there's a machine spot welding right now. Obviously, we've come a significant distance from the video I was showing you in the 1970s, and we need to have the suite of solutions to help us do that. You'll also notice that we can simulate multiple robots at the same time and multiple things going on with this fixture here as well. The product is used for material handling, equipment planning, and sequencing. And in just a second in this video, we'll get into some really complex processes as well that we're able to simulate as this finishes up a couple of spot welds that it's doing here. So here's one that really interests me that was optimized using the Process Sim software. One thing you'll notice is that the robot on the bottom, its rail is not square to the room or even square to the parts it's working with. That's because we optimized its movement path. So of course, as I mentioned, Process Sim supports multiple robot simulation, programming, execution, offline programming. All of those things can be done in the product. Again, this is just another example of how complex it can be with Process Sim, that this is an individual processes. One of the key bullet points I mentioned earlier was ensuring your robots don't hit anything or they're moving exactly the way you should. And so you simulate your plant floor in this particular area. You see that there's safety fencing in there, just to name one individual item that you need to ensure these robots are working within. So what we have here, this initial view that you have on the screen starts with two views shown at the exact same time. The upper left is a view of the actual operator HMI. This is the same set of screens that the operator would have on the production floor. And behind this view is Process Simulate itself. It's important to note that both are connected to the PLC through an OPC connection. And during the simulation run, the simulation and devices within the simulation will be communicating directly with the PLC, enabling an online debug and instant visual confirmation of cell behavior that we know is just so important. So it's interesting that you can actually simulate what the HMI will look like as well for this, and very important. So a case study that we've done with Process Sim. Obviously, I showed you a number of videos of some of our simulations we've done, but one that was really successful, this is a more recent one, of a virtual commissioning project, was at Kuka Systems in Brazil. This is one of the major line builders in Brazil, which build robotic lines for major OEMs such as Ford. Their first implementation of virtual commissioning was on a typical robotic zone, including 8 robots performing various tasks, as you see on the screen here. The challenge was to run a full project starting from initial planning to virtual commissioning. So on the plant floor, what we had to take into account were 2 robots that did adhesive application, 1 robot that did material handling, 2 that did roller hemming, and 3 that did some respot welding. And again, the challenge was full planning for this particular line in virtual commissioning. So using the virtual commissioning environment and Process Sim, the success was beyond our and their greatest expectations. Engineers from different departments all came together in the same lab and same environment, full collaboration, achieving efficient debugging of the PLC code, HMI, and safety and interlocks. All this was performed long before any actual equipment was ever installed. So when we got to actual commissioning, real commissioning, it took an unprecedented record time of just 6 hours, achieving a high-quality prototype on the very first try. Again, that's not even close. Typically, it's a week for real commissioning, at least for something this complicated. And what we got out of that was 30% less engineering time was spent on the very first project. So again, from just a digital version of what this layout's going to look like to real commissioning in the end where we set it all up, it was just a 6-hour process to set it all up because we had already debugged the PLC, everything like that. So this is a project in particular that's really, truly near and dear to the Walt family of companies' hearts because so many different aspects we worked on this project. Obviously, you recognize the vehicles on the right. And our challenge that was laid out in front of us was to add a third vehicle style to the existing 2-style process. And naturally, because it's the automotive industry, we had to increase their production by 15%. It was a heck of a challenge laid out. And during our initial assessment, we found many things. There was limited floor space. But most importantly, the plant was running 3 shifts, allowing for minimal time for field checks and as-built. Obviously, this is not an instance where there's not a manufacturing and we're building from the ground up as before. There's already one in place. So how do we measure all this information to create an accurate model? There were also multiple system bottlenecks. It was a manual process, and we had to account for adhesive cure time as well. So what was our solution? Our solution was we went in and did a laser scan of the work area to quickly and accurately capture the plant environment in 3D without disrupting any of their current production. As I mentioned, they worked full 3 shifts, so we couldn't interrupt any production. We processed, designed, and simulated the new flexible design for a seamless tooling changeover using the Process Sim software, the digital twin. The results of this project ended up being that we had successfully added a third style. We increased throughput by well over 15% actually, and we decreased operator headcounts as well. Not as many people were needed to efficiently run this plant. So the next product we'll talk about is Mechatronics Concept Designer that you see here displayed in the video. And like I said, there was some overlap in what these key things that each product hangs its hat on. And I'll explain the difference between this and Process Sim. So what you see on the screen here is an example of MCD, I'll call for short. And what you see is a 6-station rotary. So parts go around, each machine does something different. The PLC code is running and driving the simulation as you see on the right. Essentially, this is the software version of the PLC. Mechatronics Concept Designer is the CAD design tool, it lies within the CAD design tool NX, and it's similar to what is done in Process Sim that we talked about just a minute ago, because we're talking about an individual process here. However, the difference between MCD, what we're seeing on the screen here, and Process Sim, which was on the screen a minute ago, is that MCD includes kinematics. So it's an integral part of setting this tool apart with some different value. Process Sim does not include any kinematics at all in it. So I brought you back to this slide because I want to show you the video that you'll have to take a close look at inside the crystal ball. First and foremost, there's a Gantt chart up in the upper left-hand corner scrolling across. But what you'll notice is this is obviously some packaging being done here in this particular simulation. And as I mentioned, kinematics are a huge part of Mechatronics Concept Designer. So once this box is filled, it'll go on. You'll see that we have 2 folding rails here. And all we've done is just push this box down the line to push it further. But you'll notice the folding lines in the box interact, and eventually gravity will take over, and those lids will close shut. And this is a huge part of Mechatronics Concept Designer, as I mentioned. And as this video proceeds along, you'll see that there's folding rails that will fold the box the other direction. So that's just a brief little demo and video I like to show explaining or demonstrating the kinematics part of MCD. So here's MCD again here on the right, and on the left you'll notice this is the actual HMI, again simulated in the digital twin. The digital twin is your plant floor simulated, and what's great about this is you can make riskless tests. As you see on the right, that tool has crashed Obviously, we're much happier having that happen here simulated in our virtual world than we are actually on the plant floor, as that would take time and money to repair, certainly. So again, this is just run through a bunch of different examples as parts of what MCD is. At the conclusion of today's presentation, I'll have my contact information. If you're interested in seeing more about this particular product, this is brand new to our suite of solutions, and we're really excited about it and are happy to show you more and talk to you more about this. Obviously, this is demonstrating just a few of its many capabilities. The next product we're going to talk about is variation analysis. And as I mentioned at the beginning, this product is a Walt Onan expertise is where a lot of it lies. And we'll start by talking about some things that I'm sure many of you will recognize, and that's recalls that we've all heard about. So obviously, GM was engulfed in this horrible recall that had to do with the ignition switch causing the cars to combust or blow up because of some issues. So what exactly happened? Well, this resulted in 13 deaths, $1.5 billion in recall costs, 26 million cars were recalled to be fixed. And then this is a huge statistic, that GM had to provide 52 million loaner cars. That means they flooded the market with 52 million used vehicles because of this issue that they had. I'm willing to wager, and I do know for a fact, that they wish they had had a crystal ball to see problems that could occur before they actually happen. And that's what VSA does, or VA, variation analysis, does. It allows you to see these issues before they actually happen. So what was the problem? What made it combust? Again, it was the ignition switch, but I could get into the nitty-gritty engineering details, but what you need to know is this. It happened to do with this particular plunger in the ignition switch. And the distance between life and death for those people was 1.5 millimeters. If GM had properly run a variation analysis on this particular part, they would notice that just a change of 1.5 millimeters would have made a huge difference and could cause very serious problems that they obviously experienced. Here's a second recall that I'm sure we all know about. This is the Toyota recall. And this began with a Lexus crashing, killing all 4 people in a vehicle because the accelerator pedal got stuck. This was the floor mat. Is it a floor mat issue? But one thing was certain, the accelerator pedal was getting stuck. But most importantly, or I guess not most importantly, but a huge business impact that Toyota received, and I'll talk more about in a second, was January 26, 2010, they had to completely suspend sale of their vehicle and production. You can imagine what financial distress that puts on a company if you're talking about completely suspending sales and production. So here's some more statistics about, and I'll show you what went wrong in just a minute. There were 6 plants in North America alone that had to be completely suspended in their operations, 2 in Canada, 4 here in the United States, because of this issue. So what happened, and how could it have been prevented with the digital twin and crystal ball? The problem is that interlocking plastic teeth designed to provide small amounts of tension on the pedal jammed together when there was just a little bit of moisture. You can see that there's a lot of friction between the yellow and blue part at the top. Again, this caused the pedal to get stuck and not release. So what was the fix? And this blows my mind. The fix was to install a tiny metal reinforcement bar behind one of the teeth components to reduce the tension and excess friction caused that would make it get stuck. This tiny little metal shim, I guess, that they put in there, it was a 4-cent fix to make that tiny little piece of steel that they put in there. 4 cents. And you're talking about millions of dollars lost and lives too. Here's another example of VSA, and this is actually the software running to kind of give you a demonstration of what it looks like. This is a shifter assembly. So of course, when we want to take our car from reverse to drive, we want it and expect it to be in drive every single time. Well, we need to run a variational analysis on this part and experiments to see exactly how much movement we have in all the components. As you can see, this is running and the parts are moving a little bit. I don't know how smooth the video is on your side, but I can see them move. And from that, we get this graph. I certainly don't want to get into too much of the details about what it needed to be, but you could see there's way too much red in that graph. That's not going to work. There's way too much variation between the parts. But the power of variation analysis, it gives you this chart that tells you what the biggest contributors are to the problem. You can see there's a cable bracket that causes 47% of the problem. Now that we know that, we can go back in there and redesign or fix that particular cable bracket to not have as much variation. That's substantial information that it gives us, and it lets us know everything that's a contributor to a lot of the variation in this part. Again, this is truly your crystal ball, and you do this simulation on your design well before you produce this at all, because you don't want to produce a part or parts that have problems. So you can prevent that with the digital twin. This is a company I'm sure many of you recognize, and as you can see, we've been a part of many VSA or VA projects. This one is in the medical industry for Ethicon that I know I'm sure all of you have heard of before. So the challenge was to improve quality and feel of the tool of this stapler, the surgical stapler, working smoothly in the surgeon's hands. And what we had to do, obviously, this is very important. We had to assure 100% success of all staples correctly aligning. I mean, again, this is with people, this is in surgery. It's vital that this is correct always and precise too. So what were the results of business impact? Through multiple iterations of improvements, BSA showed that all the staples aligned 100% of the time before this part was ever built. And an added benefit that we found was in prior builds, Ethicon, when developing their prototypes, would order 200 sets of parts or components that they needed, and that would make just 1 or 2 working prototypes. And they'd have to mix and match parts until all the parts actually fit together and work correctly. Think about how many parts were wasted in that. And once they used variation analysis and on this program to develop those parts, all 200 working prototypes were created correctly the first time, because all the parts would go together, because we saw problems before we actually created the parts in BSA. And this is the final one that I have for BSA is in aerospace. Obviously, it's very important that when the flaps come down on wings, it's very important that this deploys correctly and there's no binding, and also that there's consistency from wing to wing. And BSA or VA is about consistency between parts. And I know all of us, when we're on a plane, we expect these flaps to come down properly every time. And if they're off by just the slightest amount, that can cause the plane to turn in a direction the pilot's not going to be real happy with. So consistency was huge, and that's why you run variation analysis on all your parts to ensure that they're correct before you even build them. So the result in business impact was the analysis exceeded expectations by a factor of 10, and there was one hole that was the largest contributor of variation from part to part. One individual tiny hole, as you can see, was the difference. So the value was this 2-week study we did, it only took 2 weeks, was savings of about 1.2 million euros in retooling. The final product we're talking about today is dimensional product validation, or DPV for short. So what you see on the screen here is a standard CMM inspection of a part for inspection and quality control. And we'll get this into the software in just a second. This is what I was talking about earlier, that from the engineer out on the floor that's running the quality inspection to the CEO, he can pull up these graphs and see exactly the quality of every single part going out the door through these different charts. You'll see a chart here in a second that's the trace field compare that compares from part to part the differences in each one that we're going to click on in just a second. There it is. This is the trace field compare. So it's so important. We now have visibility across our entire plant to know the quality of every single individual part that leaves our plant. And that's huge, and a huge change, and very important to the future of manufacturing, that we know exactly what these are. So my case study that is in fact a current and recent one that we're still working on. And this is for an automotive part supplier. So where does DPV, where's the value really in this particular, this tool? So the challenge was the supplier made the parts in plants all over the world. So a different part in a different plant. But the parts were never actually assembled until they got to the OEM facility. So problems of part fitments weren't discovered by the supplier. They were discovered by the OEM. So obviously the supplier was always in poor favor with the OEM because the parts didn't consistently fit together once you apply variation, obviously, as you can see from the pictures on the right. So we used the DPV solution to measure the parts worldwide and compare build variation from each plant and from part to part even, and predict if problems were going to happen at the OEM plant. So we were able to predict if parts would not fit together. So these problems were then identified before shipment ever took place, and corrective actions were immediately taken. So now the OEM never knew that there were any problems with these parts, because the OEM would get them and they'd all fit together the very first time. And the supplier has gone from being in poor favor with the OEM to, in fact, very, very good favor. They're one of the leaders as far as that goes now, just because they implemented the digital twin solution, DPB. So I come back to what I said in the beginning. There's so many industry drivers you face of compressed timelines. You have to lower costs. You have to increase quality, and you have to innovate. And there's engineering concerns such as validating your processes. You have to worry about cost overruns, production targets, launch delays. You need to enhance your flexibility. How do you mitigate your risks that are risks to all of these things? These are risks to you not becoming an industry leader in what you do. How do you mitigate them? And our recommendation is the digital twin. This is where manufacturing is going, is this digital realm, the digital enterprise, if you will. And you see that there's so many different products that enable the digital twin in that realm. We talked from plant simulation that simulated your entire plant, from products coming in the door to them leaving on semi-trucks, to process them in individual processes that you do, all the way down to quality of individual parts that go out your door. So the digital twin is your crystal ball that lets you see problems before they happen, I add, and mitigates risk. So again, the digital twin is your crystal ball that lets you see problems before they happen and can help you mitigate risks and the risks you're facing and concerns you're facing day in, day out that are affecting you and your industry. So with that, I'd like to thank you for your time today. I'd like to thank C&E Sales for bringing myself and Geometric Solutions in to do this presentation. My contact information can all be found here, and I encourage all of you in attendance today, do not hesitate to reach out to me with questions. If you're interested in seeing one of these products in more detail, we're happy to do so. One thing I didn't mention in the beginning is not only do we sell these products, we do support projects with them. So if you are interested in having your plant simulated or to solve problems, we can certainly do that too. So please don't hesitate to reach out. Any questions about this? I believe you'll be supplied with this presentation upon its conclusion as well, and my information will be included in that. So again, I'd like to thank you for your time today, and I hope you have a great day. Thank you.